Alright, welcome back to another fresh vid. So in this video, we're going to talk about the comparison test. We've moved on to section 11.4. In this section, we cover the comparison test and the limit comparison test. And while the names are confusing because they sound like they should be the same, there are some subtle differences between them that is going to make one of them more useful in certain situations than the other, and vice versa. So to kick this section off, let's talk about a series. And let's just consider whether it converges or doesn't converge, right? So our question is, does the series, starting at 1, 6 raised to the n power over 5 raised to the n power minus 1, converge or diverge? And it's hard to tell with our current methods, except that if we could compare it to a known series, we can infer whether it converges or diverges. So here's what I want you to notice, since we're building intuition still. Except for that pesky minus 1, it almost looks like this should be based off a geometric series where the common ratio is 6 over 5. Okay, so that part right there makes us think that maybe this diverges. We don't know, and it's hard to tell unless we, go out and play around with it. But let's see if we can find a comparable series. So here's what we want, right? We want 6n over 5n, or 6 to the n over 5 to the n, I should say. And we know that that has to be less than 6 raised to the n over 5 raised to the n minus 1. Is that true? That is not true. The opposite is true. Okay, that's not a problem. Then we'll have to find some other relationship. So let's see. Let's see if this bears out. Well, let's just plug in a 1, right? So 6/5. Then we have 6 over 5 minus 1. So 6/5 is, that's like 1.2. And 6 over 4, no, that is larger. That's like 1.25. No, it does bear out. I was right. Okay. So you want to make sure that the inequality is going in the right direction. Here's why. So scratch work aside, right? What we want is we want our original series, right? So a sub n to be either larger than or greater or smaller than the terms of another series, because we're going to compare the two series in the long run. So here's why this matters. So we know the series from 1 to infinity of b sub n diverges because of what reason, right? It's geometric with a common ratio greater than 1. Its absolute value is greater than 1, but it is also greater than 1. Okay, so because that's true, then if we were to compare all the terms of b sub n, which are less than the terms of a sub n, and add them all together, and that diverges, what we end up with is a picture that looks something like this. So we would have our b sub n, and I'm, of course, this is not a picture of the specific example that we're looking at, but more like it's a general idea. So think of it more or less as a graph, as more of a illustrating diagram. Okay, so our a sub n gives us the red bars. Okay, the values of the terms correspond to the areas of the rectangles, and b sub n is the smaller rectangles. They're smaller because the terms of the series are smaller in magnitude, and you can see that the area that's blue is contained within the area that's red. And because the area that's blue is infinite, and that implies that the red area must be infinite as well. In other words, therefore, our original series must diverge. Now, this is very loose and hand-wavy, but this is the general idea behind the comparison test, which is that the logic that we want to be true here works out. If we can find a series that has terms smaller than the series that we're working with, and that series diverges, that means your original series, the one we actually care about, must diverge. Okay, so let's actually state the theorem. Okay, the theorem. We have fewer caveats than we did with the previous test, the integral test. All we need here is, we suppose the series a sub n and b sub n, starting at 1 or 2 or whatever, but they have to start at the same point. Let's just say they start at 1, have positive terms. Then there's two cases here, right? So case 1, if a sub n is less than or equal to b sub n for all n, and the series b sub n converges, the series a sub n must also converge. So let me pause here and let me break down what that means, right? So if we're thinking about blue area versus red area, right? So these b sub n, right, are going to contribute some areas that we're going to call them the blue areas, right? For each term, we get an area of a rectangle. And if that series converges, then we're saying the complete collection of those areas must be finite together, right? So because this series converges, that means the area is finite, and that means that the original series we're working with is also finite, so it also converges, right? There's a second case, which is the case that we actually explored in that first example, which is if a sub n is instead greater than or equal to b sub n for all n. Okay, this has to be a consistent pattern the entire way through. And the series b sub n diverges. So does the series a sub n. Okay, so this is saying the opposite now, which is what we saw in that first example. We found a comparison between the original series and some new series, where the new series, right, is contributing these areas, one for each term. You add them all up, and you get the full series, and it gives you an infinite sum. So it diverges, right? Because a sub n is greater than b sub n the whole way through, then that means the contributing areas were larger all along, and so the series itself must also be larger, and so it diverges as well. Okay? So that's our justification. It basically is saying that our sum preserves the inequality. So in some sense you could say, right? And in another sense you could say, oh, well, these are too far apart for me to say. But basically, the logic that we want to bear out in the picture bears out when we actually go and show this concretely. So how do we actually use this test? Remember that it's a test of convergence. So we have some series that we suspect either converges or diverges. So step one, make a conjecture about whether the series that you're looking at, A sub n, converges or diverges. You won't get it right every time. In fact, that's part of the process. As you are working through these problems, you will build intuition. So for instance, that previous series that we looked at, we just saw that part of it looks kind of like it would be coming from a geometric series, except for that -1. And so that is what you want to examine, and you want to compare it to series that you've seen in the past, right? Or look at the dominant behavior of the series. That's going to be more important for the next kind of test, but it'll still help you here. So make your conjecture. Don't be afraid of being wrong. That can also lead you to the correct answer if you keep working at it. So if we suspect it converges, so I guess this is 2a. If we suspect convergence, find some b sub n with larger terms that converges. So does that make sense? You're bounding it from above with these terms that give you that guarantee you that you have a finite sum. So bound from above with a finite sum. B, if we suspect it diverges, so divergence, find some b sub n with smaller terms that diverges. So those are the only two cases that we're going to get, right? If you happen to get the inequality in the wrong direction, right? Or if your step 2 doesn't bear out because you didn't find something that diverges or converges when you needed it to, you want to go back. So step 3 is if step 2 fails, try again. And that can mean either going back to the very beginning and making a different conjecture. The nice thing is you're either wrong or you're right the first time, right? So there's really only two directions to try from there. And it's the second step that usually is going to cause you the more trouble, because you want to find a series that's going to be helpful in showing what you want to show. And you just have to get the inequalities in the right direction. So let's do an example. Does the series, starting at 1, 2 over square root of n plus 2 converge or diverge? Okay, looking at this, not sure where to go, but I do see that there's some dominant behavior here. So let me write this a little neater. So the numerator is a constant term, so that's not adding too much. But in the denominator, I'm changing the terms by square root of n plus 2. It looks like the dominant behavior is something like 1 over square root of n, okay? Or something involving square root of n, okay? So here's where we're going to go. We suspect it diverges. Why? Because if we compare it to 1 over square root of n, we know that that's a p series with p less than 1. And in the previous section, we saw that that is a divergent series. So if we can compare it to that, that works out. So here's something cool though. if we want to compare it to something like that. So for instance, let's compare to we're going to say the series n equals 1, 2 over square root of n. Okay. The 2 doesn't matter, right? Remember? This will still diverge. If you're unsure about why that must be true, we can talk about that in a later video. But take my word for it, this does diverge. It's certainly larger than 1 over square root of n, right? The terms are larger than that. But does this bear out, right? Is this what we want? So for instance, claim 1 is that 2 over, sorry. Let me just go ahead and write it symbolically, right? We want a sub n, the original terms of the series, to be larger than b sub n, or at least as great as. Okay, is that true? Well, we have a sub n being 2 over square root of n plus 2, and b sub n is 2 over square root of n, okay? And so because we are dividing by something, that is positive, right? All the terms are positive. So you can look at, if you're ever unsure, you can plug in the first two values, or one value if you want. So if we plug in 1, we get 2 over 1 plus 2, and 2 over 2. Okay, so this is 2/3, and this is 1. So in this case, we have, sorry, wrong way, this relationship, okay? Should we see another term? What about 2 over square root of 2 plus 2, and 2 over square root of, oh no, I'm sorry. Hang on, let me start over. So remember, the question is, which way does the inequality go? The first term, just kidding, is 2 over square root of 1 plus 2, which is 2 over 3. This first term is 2 over square root of 1, which is 2 over 1, which is 2. Yeah, that bears out like that. That's right. 2 over square root of 2 plus 2. Well, that's irrational, so we're not going to get too much out of that. But we know that it's going to be something like 1.4, 1.6-ish, okay? So it's roughly 2 over 3.6-ish. Compare that to 2 over the square root of 2, which is roughly 2 divided by 1.6, right? Divide by something larger, right? You get something smaller. So that keeps bearing out. It looks like the direction of that inequality is this way. So what's the problem here? This doesn't necessarily help us because if this is the divergent series, right, the inequality is going in the wrong direction. All right, so we're gonna have to try something else. So new try. Here's something that's helpful, and I did a little bit of preparation for this, so I just wanted to show you that you could go the wrong way. For n larger than or at least as great as 4, your a sub n being 2 over square root of n plus 2 is larger than 1 over the square root of n. This is different than the b sub n that we had chosen earlier, which is the 2 over square root of n. And the reason why this is so helpful is because, so first of all, this is going to give us 1 over the square root of n, which is a divergent series, right? But it starts at 4, okay? So in other words, because this series diverges, okay, so does the series starting at 1. Okay, let me pause and say and go over what we mean by this, okay? So why does it matter if we go out a few terms or not? In the case of a divergent series, right, we're saying b sub 1 plus b sub 2 plus b sub 3 plus b sub 4 plus b sub 5 plus dot 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 is infinite, right? So roughly speaking, and I hate to say this, right, because this is not a good way of writing it. Roughly speaking, right, this sum is infinite. And we're starting at b equals 4, n equals 4. That is infinite, okay, that diverges. If we add on a few terms, of course it's still infinite. We haven't taken away anything. We're just adding to something that's already infinite, so of course it's going to diverge. Okay, so because this series diverges, so does the original series that we want to actually use. Okay, so by the comparison test, since a sub n is greater than b sub n for all n greater than or equal to 4, and we've shown that the series of b sub n starting from 4 or starting from 1 diverges. The series that we started with, right, diverges. So you'll see that there's some fudging that we might have to do sometimes. The important part is, can you get an inequality in the right direction? And is it a series that you know how to work with? Because this test is a little bit more finicky than the limit comparison test, we'll find the next not the next section, but the next video in the section to be a little bit more intuitive, I'd say, even if the reasoning behind the limit comparison test is, I think, less intuitive than the reasoning for this test. So, in conclusion, right, what are your steps? You make your conjecture, either converges or diverges. Find an appropriate series, right, that converges when you want a sub n to converge, or you want to show that it converges, that has larger terms. If you want to show that a sub n diverges, you find another divergent series with smaller terms. And if neither of those bears out, you go and try again. And sometimes we do have to do some sleuthing to find where to start the comparison, because sometimes it won't happen immediately at n equals 1. Okay, but usually that's not an issue, because again, remember, with series, everything that matters is happening in the tail.